In this video, we'll be solving these three limits. First, we'll start with the limit as n approaches infinity of n raised to the 1 over n power. Now we can rewrite n to the 1 over n power as e to the ln of n to the n 1 over n power. And that is because x is the same thing as e to the natural log of x. The e and natural log functions are inverses. So whenever you compose inverses, you get the identity, which is x. Okay, next I can move the 1 over n exponent in front because the log brings the exponent in front. And so I can take the limit of e to the 1 over n times ln of n instead of taking the limit of n to the 1 over n. And the limit could go on top of the exponent. So instead of taking the limit of e to the exponent, I could take e to the limit of the exponent. And so the exponent can be rewritten as ln of n over n. Now, if I approach n from infinity, ln of n and n both go to infinity. So I do have to use L'Hopital's rule. And so the derivative of ln of n is 1 over n. The derivative of n is just 1. So this limit simplifies to e to the limit as n approaches infinity of 1 over n. And if I let n approach infinity, 1 over n approaches 0. So I have e to the 0, which is 1. So my limit is 1. Okay, now we're going to use the previous limit to solve this one. So I'm given the limit as n approaches infinity of n raised to the 1 over n squared power. Now, I'm going to compare n to the 1 over n squared with n to the 1 over n power. 1 over n squared is smaller than 1 over n, so the smaller exponent will be, the smaller the exponent, the smaller the value of the expression. So n to the 1 over n squared is smaller than n to the 1 over n power. Similarly, 0 is less than 1 over n squared. We know that 1 over n squared approaches 0, but never reaches 0, and it's always going to be positive, right? So it's always above the x-axis. So same argument here, the smaller the exponent, the smaller the expression. So n to the 0 is going to be smaller than n raised to the 1 over n squared power. And so we have an upper bound and lower bound for n raised to the 1 over n squared power. And now I can take the limits of each of these three expressions. N to the 0 is just 1, so I could have just simplified it the whole time and put it as 1. So the limit of that is just 1. And the right-hand limit is also 1. And that's what we did in the previous problem. So we have the lower bound being 1, the upper bound being 1. By the squeeze theorem, the limit has to be 1. Now for the final problem, we'll be looking at the limit as n approaches infinity of n factorial raised to the 1 over n squared power. But before we can solve this limit, I want to compare n factorial with n to the n power. So n factorial, by definition, is n times n minus 1 times n minus 2 times all the way down to 1. Versus n to the n power is n times n times n, n times. So they both are multiplying by the same number of terms, the n factorial and the n to the nth power. But notice, the n to the nth power is n throughout. You're multiplying n throughout, versus n factorial, you have to multiply by the next number, the previous number rather. So it's getting smaller and smaller every time. You're multiplying smaller numbers, which means that the whole product has to be smaller. And therefore we say that n factorial is smaller than n to the n power. Next, we're going to make that substitution. So we know that we're going to leave 1 over n squared as the same exponent, but because n to the n is bigger than n factorial, we know that n to the n raised to the 1 over n squared power is bigger than n factorial raised to the 1 over n squared power. And I can simplify n to the n to the 1 over n squared power as just n to the 1 over n power. So that would be an upper bound. Now for lower bound, I know that n factorial is always going to be bigger than or equal to 1 when n is bigger than or equal to 1. So keep in mind here, we're looking at n approaching infinity, positive infinity rather, and that's another way of saying like n large, right? So for large n values, we know that n factorial is greater than or equal to 1. So I'm just going to replace n factorial with 1, and because the base is smaller and the exponent is the same, we know that 1 to the 1 over n squared is definitely smaller than n factorial raised to the 1 over n squared power. So now we have an upper and lower bound. We're going to take the limit of everything. Now the limit of 1 to the 1 over n squared power, well, 1 over n squared goes to 0. So you really have 1 to the 0, which is 1. And the right hand side, we have limit as n approaches infinity of n to the 1 over n. That's also 1. So it's bounded below by 1, bounded above by 1. Therefore, by the squeeze theorem, we say that the limit as n approaches infinity of n factorial raised to the 1 over n squared power also has to be 1.